Hello, I hope you're doing well. Today we're going to continue talking about stars and how we measure the brightness of stars. We looked a little bit last class about how we measure the distance to stars using parallax and using parsecs. And then towards the end of class and for the assignment, you started to get into using distance to learn about brightness or learning brightness to compare distances. We're going to kind of expand on that brightness bit today and talk about how we measure how bright stars are. So, before we go any further, take a second, look at these questions, pause the video, talk with somebody you're sitting near, and review, think of from last class. How many light years are there in 1 parsec? What does parsec even mean? If a star that is twice the distance to a similar star, what are the relative brightnesses? One star is 2 times farther away. How bright are they compared to each other? And 4, what is a standard candle? So go ahead and pause for a second, talk with somebody you're sitting near, or in your head, think what your answer to these questions are. And then when you think you've got it, go ahead and hit play again, and we will go over these. So, to start off, how many light years are in a parsec? Remember that parsec is a measurement of distance, even though it sounds like it should be time because it's got sec for second in there. Parsec is a distance and it is 3.26 light years. Remember that parsec, the definition is parallax second. It is a distance to a star that would create a parallax angle equal to 1 arc second. There are not any stars that are 1 parsec away from us. They are all farther away than that. So we don't have any parallax angles equal to 1 arc second. The closest star to us, Alpha Centauri, is about 4 light years away, so just a little bit farther than a parsec, but that means it's got a parallax angle of even smaller than 1 arc second. Remember, the table that we looked at last class had all of those different angles, and they were all tiny decimals of arc seconds. So a parsec is really far, and a lot of stars are much, much farther than just one singular parsec. Third, if a star twice the distance from a similar star or a star that is twice the distance from Earth as a similar star, what is the relative brightness? This is getting into that inverse square law that the assignment last class was about. Distance and brightness are related by the inverse square of the distance. So here, one star is 2 times farther away. That means I have a distance factor of 2. 2 squared is 4, and it's inverse. So it is 1/4 the relative brightness. So the star that is farther away is going to be 1/4 as bright. And then lastly, we kind of in that assignment got into the idea of a standard candle. A standard candle is a star or a nebula or a supernova or a galaxy or something in space. It can be anything in space, but something in space that we know how bright it is. We know for a fact exactly what the brightness of this object is. And so we are going to use it as a comparison tool. Think about a ruler that is exactly 12 inches long. I can pick up a ruler, any ruler, and without looking at it, know that if it's a standard ruler, it's 12 inches long. And I can compare that to other things then, right? I use the ruler to measure other stuff. A standard candle is the same idea. It is an object with a known brightness. It is 12 inches long, and I'm going to use it to compare other things. So, a standard candle, that object in space, again, can be anything, a star, a galaxy, a supernova, but we know how bright it is, and we're going to use it as our ruler, as something to compare to. So here is, again, that inverse square law. Remember that light, after it leaves the object, the light bulb, the candle, the star, the galaxy, it goes out in every direction. It is spreading out in length and it's spreading out in width. So it is moving out in every direction, getting bigger as it goes. So, really, since it's spreading out from our point of view in both length and width, it's spreading out over an area or a length times a width. So that's where we get the square from. as I go farther away, my distance is increasing by whatever my distance factor is, but the area that I'm receiving light over is going by something squared because it's an area. So if I am a distance of 1 unit, maybe 1 light year away, I'm seeing a brightness of 1. But if I move 3 times farther away, now that same light has to be spread out over 3 squared, or 9 times the area. So this inverse light curve is showing me that as the area gets bigger, I have to account for how much area I'm spreading out over, which is why it is that distance squared. So let's look over kind of some of the questions or types of questions that you maybe saw on that inverse square assignment from last class. If you didn't finish that, take some time to finish it today. If you feel like you did it, but you weren't super sure how you did, you have multiple attempts at it. So if after going through these questions, it makes more sense, go back and look at it again sometime today. So 1, I've got 2 stars that are at a distance of 10 light years and 30 light years, respectively. What would the relative brightness be between these 2 stars? So I've got one that's 10 light years and one that's 30 light years. I don't care about the exact distance. I care about the distance factor. How far off are these two from each other? So I'm going to take the farther object, the 30 light years, and divide it by the closer object, the 10 light years. And 30 divided by 10 gives me a relative distance, or a distance factor, of 3. One object is 3 times farther away than the other. Now I do 3 squared, or 1 over 3 squared, and I get that the farther away star is going to be 1/9 the brightness. So remember, farther away, it's going to be dimmer, right? The farther away from a light you are, the less bright it looks. So I've got 1/9 the brightness. Number 2, I've got one star that is 5 light years away, another star that's 25 light years away. Same idea. What is the relative brightness? Pause right here and see if you can figure out for yourself. The farther one is 25 light years away. The closer one is 5. So 25 divided by 5 gives me a relative distance, or a distance factor, of 5. The farther star is 5 times farther away. 1 over 5 squared gives me 1 over 25. So the farther away star is 1 over 25 times the brightness. So it's much, much dimmer. Sometimes we want to work it the other way, though. Sometimes we can tell how bright they are comparatively and want to use that to find distance. So here I've got a star that is known to be 15 light years away, and it is 16 times brighter than a similar star named Theta Cygni. Theta Cygni is a real star. It is in the constellation Cygnus, which is the swan. So what is a reasonable estimate for the distance between Theta Cygni and Earth? If the closer star is 16 times brighter, that is my distance factor squared. So in order to kind of undo this, I got to go backwards. I got to take the square root. The square root of 16 is 4. So there's going to be a distance factor of 4 here. Now I need to figure out if Theta Cygni is going to be closer or farther away from Earth. Well, farther away stars are going to be dimmer, and closer stars are going to be brighter. And it says that the star that is 15 light years away is brighter, which means Theta Cygni will be dimmer and will be farther away. So if it is 4 times farther away, I need to do 4 times 15 to get a distance of 60 light years. One more example problem like this. I've got Kappa Orionis, a star in the constellation Orion, is about 650 light years away from Earth. There's a similar star that has a relative brightness that looks 36 times brighter than Kappa Orionis. What would be a good estimate for the distance from that star to Earth? So same kind of thing. I have a distance and a brightness factor, I need to kind of work backwards here in order to get another distance. So 36 times brighter, the square root of 36 would give me a distance factor of 6. I know that my face is covering some of this. These slides will be available to you if you need to go back and look at them. So I'm going to work backwards to get the distance factor of 6. So one star is going to be 6 times farther away than the other. No, I need to figure out which direction again, which one is closer. The similar star is brighter, and Kappa Orionis is 650 light years away. So the similar star is going to be closer, which means I need to do 650 divided by 6 to get my distance, which gives me a distance of about 108 light years. This should have been pretty similar to the problems that you saw on that assignment on Canvas. So like I said, go back and take a second look at it. Everybody's got multiple attempts on it. Use all of those attempts. I will only keep your highest score. But this is kind of what hopefully you were seeing on that assignment. So if I use that inverse square law, and again, looking at kind of this graph version of it or the visual with the area, I can use that to calculate the distance to similar brightness stars. And hopefully you noticed in those questions, I kept saying distance to a similar star. The thing is, stars come in a lot of different shapes and sizes and flavors. This is one of the astronomy pictures of the day, which is a cool website by NASA that just has a different fun space picture every day. And you might notice, 1, there are a lot of stars. 2, there are stars that are very clearly brighter than other stars. 3, there are stars that are different colors. You can probably notice this on a clear night if you go out and look outside. There are some that look more white, more blue, more orange, more yellow, and all of that means something. And we will get more into what exactly the color of a star means next week. But clearly, stars are not one size fits all. There's a lot of different variety in stars. And so we need different ways to describe how bright they are. This is the constellation Ursa Minor, the Little Bear or the Little Dipper. Hopefully it's familiar to you. It's one that we've talked about a bunch. Here's Polaris, the North Star. And you can see that each of these stars, they are listed and then they've got a little number by them. This is the magnitude of the star. This is a system that was first made by the ancient Greeks to just kind of classify how bright is a star. So Hipparchus, way back when with the ancient Greeks, was the first person to just kind of look up and be like, that's the brightest star. I'm going to call it number 1. That's the second brightest star. I'm going to call it number 2. That's the third brightest star. I'm going to call it number 3. Then a little while later, Ptolemy gave it a little bit more organization. He introduced the name magnitude. So that brightest star, I'm going to call it first magnitude. The second brightest star, I'm going to call it second magnitude. And for these guys, and for us still, the dimmest that you can see just with your eye without a telescope is around a 6. So they had 6 categories and said, yep, that's a 1.5. It's somewhere in between number 1 and 2. Not a super scientific way of doing it, just a kind of, this star looks brighter than that one, so I'm going to call it 3 instead of 4. But since then, we have refined this system and we've added mathematical formulas and we have added a lot more complicated things to make it make sense. It's still, and this is going to be something that is confusing, but I promise we will work on it together, a backward system. Because 1 is a bright star, 6 is a dim star, and in fact, as we go, we even eventually added negatives to it once this got more mathematical. So here are some common things. Like I said, the naked eye limit is around 6. With a good telescope, you can see maybe up to like 15-ish, just like a normal backyard telescope. A like big fancy telescope on the surface of Earth can maybe see up to like a 22, 23, and the Hubble Space Telescope is close to 30 is kind of the limit. Remember, a big positive number means a dim object. So Sirius, the brightest star in the sky, we've actually decided, we've kind of reworked the system a little bit, and Sirius has a magnitude of about -1. Polaris has a magnitude of about 2.5. And I think Polaris, hopefully, is not the brightest star in the sky. It's a star that is familiar to a lot of people. So it is a star that people often think is the brightest, but Sirius is the brightest. The sun has a magnitude of -26. So negative things are brighter. The more negative, the more bright. The full moon is brighter than Polaris is. So it's a backward system because a really big number like 30 means something is really dim and really small and hard to see. A really big negative number like -30 means something is really, really bright. Another star that we've talked about, Barnard's star, has a magnitude of about 9, so it's not actually something that you can see with the naked eye. You would need a telescope to see Barnard's star. And you might notice that it says down here that this is the apparent magnitude, and I've got that marked with a lowercase m. So we've got two different magnitude systems because something like Barnard's star has this low magnitude, but it's also really close to us, right? Barnard's star is one of the closer stars to us. It is a distance of like 6 light years away. And so it is dim already when it's close. Imagine if it was farther away. Sirius is a pretty bright star. I mean, it's the brightest star in the night sky, and it's pretty far away from us. Imagine if we moved Sirius closer, it would outshine a lot of other stuff. So we've got these two different magnitude scales that we're going to look at. The first one is what I was just saying, apparent magnitude. This is just, I'm going to look up into the sky and classify these stars. How bright does this appear from my backyard? No funky calculations, no anything going on, just how bright is this from where I'm standing here on Earth? Absolute magnitude is how bright the star appears if I was 10 parsecs away. If I took every star and moved it to be the same distance, if I pushed every star or pulled some stars so that everything was the same distance away, how bright would they be? And this word will come up a couple of times. Luminosity is the actual thing that we are measuring here. Luminosity is how much energy is a star emitting from its surface. So absolute magnitude has to do with the luminosity, has to do with how much energy is being put out. But we've been seeing how distance can affect the amount of light you get, right? That was the whole inverse square law, is that things that are farther away appear dimmer and things that are closer appear brighter. So absolute magnitude is like, let's take the distance factor out entirely. Let's push everything to be the same distance away. Everything is 10 parsecs away, and compare what they look like then. So here we've got 3 stars. Maybe this is Sirius, this is Barnard's star, and maybe this is Polaris. And they are all different distances away, and so some appear brighter or appear dimmer. But that would be the apparent magnitude, how they appear here on Earth. The absolute magnitude, on the other hand, is what if I move all of these to 10 parsecs away? Now I'm not accounting for distance at all. Everything is the same distance away. So I can imagine how would they look compared to each other. And for these 3 stars, for example, I end up pushing all of them farther away. So since I'm moving them farther away, their absolute magnitude is going to be dimmer than their apparent magnitude. If I had a different star that started way back behind 10 parsecs and then I pulled it closer, since it's coming closer to me, it's going to look brighter. And so it would have an absolute magnitude that is brighter than its apparent magnitude. Another common analogy that you see with absolute and apparent magnitude is like headlights or looking at flashlights and a firefly or something like that. So here I've got two identical cars, car A and B. Maybe they're both Lightning McQueen. Two identical cars, and car A is closer to me than car B is. So since these are identical cars, they would have the same absolute magnitude. But A is closer to me, so it would have a brighter apparent magnitude, and B, excuse me, would have a dimmer apparent magnitude. A different example is that same car versus a truck. If you've been driving down the road at night and you've got like a truck behind you or a car with like LED headlights, those are a lot brighter naturally than a other car headlight. So A is going to have a brighter absolute magnitude because the headlights just are brighter. They're putting out more light, and car B is going to have a dimmer or absolute magnitude. But if that truck is 20 miles away from me and the car is right behind me, the car is gonna look brighter, right? So distance is gonna play effect, and that's why we have absolute and apparent magnitudes. The constellations, where people arbitrarily drew lines connecting stars, constellations are all different distances away. And so it may seem like, oh, these are all grouped together because they are near each other in space. Really, there could be hundreds of light years or parsecs separating them, and they only appear bright because one of them's got a huge or a very bright absolute magnitude. And so, if you can think about having a flashlight right in front of your face versus a car 5 miles away, if they were the same distance, the flashlight's a lot dimmer than the car is. But if the flashlight's right in front of my face, it's going to have a greater apparent magnitude because it appears a lot brighter. Here's another way to kind of see and compare those. One thing I haven't touched on yet is the symbol. This is going to be another confusing thing, and I'm sorry, astronomers often come up with bad systems or just keep using the systems that like ancient Greeks used, even though they probably don't make as much sense anymore. Apparent magnitude is a lowercase m. Absolute magnitude is a capital M. And oftentimes you'll see them right next to each other. People will note the apparent and absolute magnitude at the same time. Today, you're going to be looking at kind of how do we use magnitude, and it won't get so much into apparent versus absolute, but you'll see how this magnitude scale in general works. The apparent and absolute magnitude scales are the same. The numbers work the same way. One is just how is the star when I view it from Earth without moving anything. The other is how would the star be if I imagine moving it to 10 parsecs. So your assignment today is going to be a worksheet that is practicing doing some calculations with apparent and absolute magnitude. I forgot to say this earlier, but I promise you that anytime you have to do calculations on a test or a quiz or an assignment with the inverse square law, you will only get easy to work with numbers. I'll only be giving you 2 squared is 4, 4 squared is 16, 36 square root is 6. Just easy numbers like that. And when you have magnitude, there are going to be a couple of kind of weird calculations. When you're working on the assignment today, the key will be available if you want to go back and check yourself and make sure that you're doing it right. Because really, I want this to make sense to you. If you have questions, like I said before, send me an email, send me a message on your mind, and I'm happy to help. Talk to you later.